Hey everyone, welcome back to SkillSync, the channel where we break complex tech stuff into simplest way possible. So today, we are going to talk about something that happens every single time you turn on your Linux system. But most people don't even realize what's going under the hood. In today's video, we are going to see the complete journey from pressing the power button to seeing the login screen. So let's get started. So today we are going to talk about something that happens every time you turn on your Linux system. Yes, the booting process. The entire Linux booting process can be narrowed down into just 4 stages. The first stage is initializing hardware. During the boot process, the computer's firmware such as BIOS or UEFI takes charge of the hardware resources like processor, memory, or storage devices. This stage ensures that computer is fully prepared for operating system's use. The second stage is loading the operating system. Once the hardware is initialized, the boot process commences with loading the operating system. This step consists of loading the kernel and initializing crucial OS services into the memory. The third stage is launching the system services. As the operating system starts, it activates various system services and drivers. These essential components ensure smooth working of the computer, enabling various tasks such as managing network connections, processing input-output, and maintaining security measures. At last, the boot process reaches its peak, granting you, the user, with a login screen or a desktop environment, granting full access to the computer's hardware resources and its various applications. Before diving into the Linux boot process, let us understand it with the help of a diagram. The Linux boot process consists of BIOS, MBR, Bootloader, Kernel, RootFS, and Init Process. The following diagram depicts the complete step-by-step process of booting a Linux system. Now let us understand each of them in detail. Alright, it all begins when you press the power button. The first thing that runs is called a BIOS or UEFI. Think of BIOS or UEFI as the system's built-in firmware, like a mini program that lives on the chip of your motherboard. The power on self-test is a diagnostic testing sequence which is carried out by the computer's firmware, whether it's BIOS or UEFI, as a crucial step in the booting process. Its main purpose is to verify essential hardware components are functioning properly before handing control over to the OS. Each component is tested to ensure its response. CPU is checked by ensuring its operating frequency. RAM is tested by reading and writing data to check its integrity. Storage devices are checked for presence and basic functionality. Any failure during the post-test results in error messages or audible beeps. Once post sequence completes without detecting any errors, the firmware proceeds to initialize further system components and search for a boot device to load the OS. For decades, BIOS has been a dominant firmware interface on a motherboard's chip, but UEFI is more modern and versatile replacement for BIOS. It works similar to BIOS but supports more modern hardware and has faster boot times than BIOS. UEFI introduced Secure Boot, a security feature that verifies digital signature of bootloader and the operating system's kernel. This prevents loading of unauthorized or malicious code during boot time. Now let us summarize the key differences between UEFI and BIOS. BIOS operates on a 16-bit interface, whereas UEFI can operate on 32-bit or 64-bit interface. BIOS supports 4 physical partitions up to 2 DB, whereas UEFI supports 128 partitions up to hexabytes. BIOS provides basic security, but UEFI provides secure boot. The performance of BIOS is quite slower as compared to UEFI. The MBR is a crucial part of the disk structure in a BIOS-based system. It is located in the very first sector of the hard disk and only contains 2 things. 1. The bootloader code, and 2nd, the partition table. When the system starts, the BIOS hands over the control to the MBR, which then loads the bootloader to kick off the OS start. MBR is located in the first sector of the storage device, that is the first 512 bytes. It's in a fixed location called as logical block address 0. The first 446 bytes are for the bootstrap code area. The next 64 are for the partition table, and the last 2 bytes are for the boot signature, the MBR validation check. It is also known as the magic number. Partition table is a small database which holds information about disk partitions. It can store information for up to 4 physical partitions or 3 physical partitions and 1 extended partitions. You can imagine of the partition table like a book. A book can have multiple chapters. To jump to a certain chapter, we have basically 2 ways. One is to serially find that chapter, and the second and more convenient way is to have an index page. The index page has the name of the chapter as well as the page number. So the partition table acts similar to a index page. So you can jump directly to a certain partition. The partition table consists of 3 things. 1. The starting and ending address of a partition. The type of the partition. The type can be like NTFS, ext4, etc. And the third and important thing is the bootable flag. It indicates which of the partition is bootable. MBR's primary function is to locate and load the active partition's bootloader. It reads the partition table to identify which partition holds the bootable flag and executes the bootloader code from that partition. Next, we have GPT, a modern alternative to MBR. GPT is used in modern devices and is closely related to UEFI based systems. It replaced MBR due to its numerous advantages and capabilities, especially in conjunction with the UEFI firmware. Let's quickly understand the structure of GPT. Each partition in a GPT disk is identified by GUID. This allows for up to 128 partitions, but this also depends on the firmware and the OS. GPT contains something called as protective MBR to maintain compatibility with legacy systems that do not recognize GPT partitions. The protective MBR basically tells the older system that the disk is in use and prevents them from overwriting or modifying the GPT partitions. GPT stores partition entries at the beginning as well as the end of the disk. You can compare this to the book example which we consider for MBR. In that we had the indexed page at the beginning of the notebook. What if that index page gets damaged? Now you don't have access to the chapters. GPT uses a modern approach where it has 2 index pages, one at the beginning and one at the end. Now even if the index page at the beginning gets damaged or lost, we still have the index page at the end of the notebook, from where we can access the chapters as well as retrieve the index page in the beginning. So this technique used by GPT ensures that integrity of our partition table and also provides backup of the partition layout. UEFI requires a specific partition known as UEFI system partition, which is the primary component of the GPT scheme. Secure boot uses the information from GPT to verify the digital signatures of bootloader and other OS components, ensuring a secure boot process. GPT supports disk sizes larger than 2 TB, addressing the limitations of MBR. It provides scalability for future needs. In the next step, we have the bootloader. In the Linux systems, the bootloader used is GRUB, Grand Unified Bootloader. It is widely used bootloader in the Linux system and is responsible to manage the booting process of Linux based systems. It is a program that loads the operating system into the computer memory during the startup process. GRUB is specifically designed for Unix-like operating systems. GRUB's primary function include locating the kernel and loading the operating system into the memory. It also manages initrd or initrd, more on that later, that aids the kernel in the booting process. GRUB uses the configuration file named as grub.cfg, which is usually located at /boot/grub/grub.cfg. By modifying this configuration file, you can define boot options and specify kernel parameters. This also includes the customization of the boot menu. This allows GRUB to take control during the booting process and present a menu interface. So this is what the GRUB menu looks like. Here you can select the operating system of your choice available on your machine. The next section is initrd, initial RAM disk. initrd is a temporary operating system loaded into memory before the original operating system takes over. It provides minimal set of tools, drivers, utilities which are required to mount the root file system. It contains the essential drivers which kernel might need to access the root file system. Once initrd is in place, the kernel executes a code within the initrd. This code performs various tasks like loading essential drivers for disk controllers, file system, initializing hardware, and performs necessary checks. This prepares the system to transition to the actual root file system. After successful initialization, the initrd hands control to the kernel. The kernel unmounts the initrd and mounts the actual root file system. Modern systems use init initial RAM file system. It's an CPU archive. CPU is basically archival technique similar to tar. Init loads compressed operating system into the RAM. Init is versatile and allows more modular approach. In the next step, we have the kernel. The kernel is a software which manages the hardware resources. It acts like a bridge between hardware and software. The kernel initializes hardware, mounts the root file system, and finally starts the user interaction initialization process. The kernel uses the information provided by the initrd to mount the file system, like the type of the file system, partition, etc. Next, we have the RootFS, the root file system. The root file system is initialized by the kernel. The root file system is a top-level directory and contains all the essential files and directories. It is the initial file system which kernel mounts during the booting process. All other directories are mounted as the subdirectories of the root file system. The GRUB is configured to specify the location of the root file system. The root file system can be of different types like ext4, xfs. This choice totally depends on system administrator's preference. The root file system contains the crucial directories like /bin, which contains the binaries, /etc, which contains all the configuration files of the operating system. Other files like /lib, which contains the libraries required at the boot time. RootFS is a persistent type of storage. That means it retains across reboots. The stability and functionality of OS totally depends on successful initialization and mounting of the root file system. Finally, we have the last process called as the init process. The init process is a fundamental part of the booting process. It brings the system to a functional state. The init process, if we consider the real-time system, it is called as the systemd, where D stands for daemon. It means that systemd runs in the background, aiding the overall booting process. It initializes the system in parallel, improving the performance and faster boot times. Systemd reads its configuration from /etc/systemd/system, which is linked to /usr/lib/systemd/system. This provides essential services like networking and logging of the system. Once the systemd is in place, it launches various daemons which run in the background and which aid after the booting process. Systemd is the first process launched by an Linux operating system. Its PID is 1. Various daemons are launched after the systemd. For networking, daemons like SSHD, HTTPD are launched. For logging, RHCSLogD daemons are also launched. NTPD is used for network time synchronization. For hardware management, a daemon called as udev is launched. That's all about the Linux booting process. Lecture notes are in the description. Thanks for watching. Now go sync your skills.